The navigation system is divided into three main groups: Air Data and Inertial Reference System, ADIRS, plus standby instruments, radio navigation, additional navigation systems. There are several subsystems within each group. The first group includes Air Data Inertial Reference Units, ADRU, Global Positioning System, GPS, standby instruments. Let's concentrate on the radio navigation group. The radio navigation group includes radio navigation aids, radio altimeters, digital distance and radiomagnetic indicator, DDRMI. The additional navigation systems include Ground Proximity Warning System, GPWS, ATC transponders, weather radar. This completes the introduction to the subjects that will be covered in the following modules. The purpose of the Air Data Inertial Reference System, ADIRS, is to provide air data and inertial information to the EFIS system, the FMGEC and other users. The A330 is equipped with three separate but identical air data inertial reference units. Each ADRU combines an air data reference computer, or ADR, and a laser gyro inertial reference system, or IR. The ADR and IR systems of each ADRU operate independently, and failure of one system will not cause failure of the other. The ADR part receives information from aircraft probes and sensors. The ADR part provides air data to the FMGEC and other users. The air data provided includes Mach, airspeed, temperature, overspeed warnings, barometric altitude, and angle of attack. The IR part provides inertial data to the FMGEC, EFIS, and other users. The inertial data provided includes track, heading, acceleration, flight path vector, aircraft position, ground speed, and attitude. The three ADIRs are controlled through the ADIRS panel, located on the overhead panel. Their initialization is done through the three MCDUs located on the pedestal, and distribution by two of the switches on the switching panel, located at the front of the pedestal. Independent data is supplied by each ADRU. Let's see an example of this. In the EFIS system, ADRU 1 supplies the captain's EFIS, and ADRU 2 supplies the first officer's EFIS. ADRU 3 is available as a standby to either EFIS system via the switching panel. Use of the switching panel will be covered in the abnormal section. Now, let's look at the Mode Selector Unit Panel, MSU. The panel is divided into two parts, the upper section for the IR and the lower section for the ADR. The three rotary mode selectors have control over both the IR and the ADR. The controls and indicators for the individual ADRU are grouped and arranged in the order of 1, 3 and 2. Each ADRU has an associated IRS rotary mode selector. In the off position, the ADRU is not energized, so ADR and IR data is not available. The three ADR and three IR switches normally remain on, but they can be selected off in response to ECAM procedures. In the nav position, the ADRs are energized. The nav position is the normal mode of operation and full inertial data is provided to the aircraft systems. The on-bat light illuminates to inform the crew that the ADRU system is being powered by aircraft battery only. The light also illuminates for a few seconds at the beginning of a full alignment as a test of the battery circuit. We will discuss this further in normal and abnormal operation modules. The AT position is an IR mode providing only heading and attitude information in case of loss of navigation capability. We will discuss this further in abnormal operations. Present position information for ADR's alignment is normally entered via the init page of the MCDU. This method will be explained in the normal operation module. The radio navigation aids enable the crew to navigate and monitor its position. The A330 family is equipped with 2 VORs, 2 DMEs, 2 ILSs, 2 ADFs.
The FMGECs can automatically tune the VORs, DMEs and ILSs for position updating and display purposes.
The radio navigation itself is controlled by both FMGECs and can be monitored through MCDU pages. Either MCDU via the radio navigation page enables the crew to manually tune a specific nav aid, including both ADFs. FMGEC auto-tuning continues normally in the background. Note that when an ILS approach is selected, ILS-1 is displayed on PFD-1 and ND-2, ILS-2 is displayed on PFD-2 and ND-1. As you have seen in the EFIS chapter, the mode selector enables the pilot to select different ND modes to display flight plan and nav aids data. Plan mode is recommended when entering and checking the flight plan. However, notice that nav aid data cannot be displayed in this mode. In all the other modes, ROSE ILS, ROSE VOR, ROSE NAV and ARC modes, the nav aids can be displayed provided the ADF VOR selectors have been switched to VOR or ADF position. Here, as an example, the ROSE VOR mode with ADF1 and VOR2 selected. ADFs are shown as green pointers, here ADF1. VORs are white pointers, in this example VOR2. Note also that the receiver 1 data is displayed on the left side of the ND and the receiver 2 data on the right side. The associated nav aid data is displayed at the bottom of the ND in their respective colors and sides. We will see the different ND modes and nav aid tuning in more detail in the normal operation module. In the unlikely event of a double FMGEC failure, the backup tuning mode provides radio navigation redundancy to the crew. The backup tuning mode is accessed via the Radio Management Panels, RMP.
For Nav-A tuning, RMP1 standby navigation keys are associated with VOR DME1 and ADF1, while RMP2 keys are associated with VOR DME2 and ADF2. Either RMP1 or 2 can tune the ILS. To access the backup tuning mode, the nav key has to be pressed.
When the backup tuning mode is selected, i.e. nav key illuminated, the control of the associated receivers is transferred to the RMP and the Nav-A tuning capability of both FMGECs is lost. This is indicated on the MCDU by a change to the radio navigation page, which shows only the titles now. To return the control to the FMGEC, the nav key has to be pressed again.
In backup tuning mode, the selection of one of the standby nav keys enables the crew to tune the associated nav aid. We will see how to operate them in the Abnormal Operation module. We will now study the Digital Distance and Radiomagnetic Indicator, DDRMI. The DDRMI is located on the main panel. The DDRMI displays ADF, VOR and DME raw data and combines a traditional RMI and a bearing pointer presentation. Two bearing pointers are provided, each with a different distinguishable shape. Each can display either VOR or ADF information. Each pointer has an associated control knob. The left knob selects either VOR1 or ADF1. The right knob selects VOR2 or ADF2. Here, VOR1 and VOR2 are selected. The compass card displays the bearing scale that is supplied from ADRU1. The counters indicate the DME distance. However, the window will only display dashes if an ADF is selected. Here, ADF2 is selected. The A330 family is equipped with a Ground Proximity Warning System, GPWS. Its purpose is to enhance safety by alerting the crew to potentially hazardous situations involving terrain collision or incorrect landing configuration. The GPWS monitors the aircraft flight path and generates visual and audio warnings alerts when the aircraft is in one of the defined hazardous situations. These warnings will be overridden by stall or wind shear warnings. The GPWS processes the data from RA1, ADIRS1, ILS1, FMGEC1, LGCIU1. Failures of these units will be studied in the Abnormal Operation modules.
Most ground proximity warning system alerts and warnings are generated as a result of changes in radio altimeter heights or the rates of those changes. The system predicts potential hazards from these trends, but has no forward-looking capability.
Therefore, impact with a near vertical cliff face cannot be predicted. GPWS does not absolve the crew from monitoring aircraft position and safety altitude. The GPWS control panel is located on the left side of the overhead panel.
GPWS visual warnings are provided on the miscellaneous panels. The system can be tested by pressing either GPWS glide slope push button switch. This test is normally performed by the maintenance crew. In addition, two loudspeakers located on each lower side of the main panel broadcast GPWS oral warnings even if they are turned off. GPWS enhances safety by alerting or warning the crew of potentially hazardous situations during flight at low heights. Crews should react to any GPWS warning immediately without attempting to assess its validity. GPWS operation is fully automatic in the normal lights out configuration. We will now study the oral and visual alerts and warnings. If a high rate of descent is detected at low level, the GPWS will generate an oral repeated
sync rate
alert. If this rate is or becomes excessive, the repetitive oral warning
all up.
will be generated. In both cases, the red GPWS lights will illuminate. If rising ground is detected as a potential threat to the safety of the aircraft, the GPWS will alert the crew with a repeated
terrain
oral alert. The system will generate a
all up.
warning after the terrain alert has been repeated twice. The red GPWS lights will illuminate in either case. If the GPWS detects a rate of descent during the initial climb after takeoff or following a go-around, it will give a repeated
Don't think.
alert with accompanying GPWS red lights. If the landing gear and flaps are retracted and the GPWS detects that the aircraft is close to the ground, it generates a
Too low terrain.
oral warning and the GPWS red lights illuminate. At very low levels, the oral warning
Too low gear.
will be generated if the landing gear is still retracted. If the landing gear is down, but the flaps are not in landing configuration, the warning is
Too low flap.
note that the
Too low gear.
warning has priority over the
Too low flap. Glide slope.
below approximately 1,000 feet on an approach. A GPWS glide slope oral and visual alert will be generated if the runway is ILS equipped, the ILS is tuned, the ILS signal is valid, the aircraft is significantly below the glide slope. Both amber glide slope lights will illuminate.
Glide slope.
The oral message will become louder to indicate a warning if no corrective action is taken as the aircraft gets closer to the ground, or if it descends further below the glide slope. Note that some airports around the world have approaches and departures which are not compatible with standard GPWS operation. These airports are programmed into the GPWS database, and the warning thresholds are modified to avoid nuisance warnings. The GPWS panel allows the crew to inhibit some warnings. Flap 3 is a recognized landing configuration. If the option is used or if required by an ECAM procedure, the crew should select Landing Configuration 3 on the MCDU to ensure that the GPWS does not generate warnings when it detects that the aircraft is not in the full flap configuration. Following certain failures, a landing may have to be made with a reduced flap setting. The crew can select the flap mode push-button switch off to inhibit GPWS flap warnings. If the flap mode is off, the green flap mode off message is displayed on the engine and warning display.
When selected off, the glide slope mode push-button switch will inhibit the GPWS glide slope warning. The white off light illuminates when the GPWS is selected off. All warnings are inhibited.
If your aircraft is equipped with the enhanced GPWS, eGPWS, a forward-looking capability for terrain is added. The basic functions we have just studied remain unchanged. eGPWS is based on terrain databases and FMGEC current position, not on radar returns. The purpose of the eGPWS is to avoid a controlled flight into terrain and to give enough time to the crew to perform an avoidance maneuver.
The terrain information is displayed on the ND except in plan mode. A different image texture, an image display which sweeps from center outward to both ND sides, and a terrain indication instead of the radar tilt indication help the crew to distinguish between the eGPWS terrain computed data and the ground picture sensed by the radar. The terrain elevation surrounding the aircraft is color-coded. 2 terrain-on ND push-button switches are fitted on each side of the main panel. To display the terrain picture on his ND, a pilot will have to switch on his respective terrain-on ND push-button switch. Note that the weather radar information is replaced even if it is switched on. In the lights-out position, the eGPWS operation is fully automatic. The terrain push-button switch in the off position allows the crew to inhibit the enhanced functions, but keeps the basic GPWS functions operative. In case of failure of the enhanced functions, the fault light comes on, but the basic GPWS functions remain operative. As for the basic GPWS, the system push-button switch controls the basic functions. The eGPWS uses a terrain database coupled with an FMGES position to calculate 2 terrain envelopes ahead of the aircraft. When a conflict is detected between these terrain envelopes and the terrain memorized in the database, an alert is triggered. One terrain envelope corresponds to a caution level, while the second one to a warning level. If the caution terrain envelope is penetrated, the areas which violate the caution envelope limits turn to a solid yellow color. An amber terrain ahead message appears and a repeated
Terrain ahead
oral alert is generated. If the terrain warning envelope is penetrated, the areas which violate the warning envelope turn to a solid red color. A red terrain ahead message appears and a repeated
Terrain ahead Pull up
oral alert is generated. In both cases, the red GPWS lights will illuminate. As for the basic GPWS warnings, crews should react immediately without attempting to assess its validity. In case of caution or warning, if Terrain on ND is not selected on, the terrain display is set automatically to on and the on light on the Terrain on ND push-button switch comes on. The second EGPWS protective function provides a terrain clearance floor envelope for each runway stored in the database. This function warns of a premature descent below this floor regardless of aircraft configuration. Caution: the relative height is calculated using the Captain Barrow setting. Thus, the system does not protect against Barrow setting errors. The position is calculated using FM1. The system does not protect against FM1 position errors. When the aircraft position accuracy provided by the FMGES is not sufficient, the enhance functions of the EGPWS are automatically deselected. Terrain Standby appears in green on the ECAM memo and the terrain display is deselected until a high level of navigation accuracy is restored. The basic GPWS functions remain operative. Two radio altimeters are installed in the A330. They measure the aircraft's height above the ground accurately. There are no radio altimeter controls in the cockpit. Both radio altimeters come on automatically when AC power is applied to the aircraft. After a brief self-test, the radio altimeters are in a standby mode during ground operations. They become active at liftoff and then operate continuously until touchdown. Radio altitude is always expressed as the number of feet between the bottom of the wheels and ground. Radio altimeter data is supplied to several different users and is displayed on both PFDs at all times below 2,500 feet above ground level. Normally, radio altimeter 1, RA1 height, is displayed on the captain's PFD and RA2 on the first officer's PFD. The radio altitude display on the PFD changes in color and size based on height above ground and or proximity to the decision height. This color-coded digital readout is coupled with a white ground indication line and a red ground ribbon on the altimeter scale. The ground indication line and the red ground ribbon correspond to the rising ground level when the aircraft is descending. As the aircraft descends below approximately 500 feet above ground level, the red ribbon appears at the bottom of the altimeter scale and begins to move up. The white ground line moves from the bottom of the PFD towards the horizon. At touchdown, the ribbon is in the center of the altitude readout and the white ground line is merged with the horizon as shown. These are designed to be used as a ground reference during auto-land operations. In addition to the visual indications, during approach there is a synthetic voice for radio altitude announcement. At predetermined heights, the announcement will be heard through the loudspeakers, even when the loudspeakers are turned off. For example, at 400 feet, a call-out of
400
The A330 family is fitted with two ATC transponders which provide responses, including altitude reporting, to radar interrogations. In normal operation, ADR1 provides barometric information to ATC1, ADR2 supplies ATC2. A traffic alert and collision avoidance system, TCAS, provides the crew with traffic information and warnings of potential conflicts with avoidance instructions. TCAS only detects and indicates other traffic equipped with a transponder. A control box located on the center pedestal allows the pilot to control the ATC and TCAS systems. The main part is dedicated to the transponder controls, while the right bottom part is used for the TCAS controls. A weather radar is installed to detect severe weather and display it on the ND for use as a severe weather avoidance tool. The weather radar control panel is located on the center pedestal. We will now look at the different controls and indications of the weather radar. The on-off switch controls the power supply. When switched on, the tilt indication appears on the ND. The tilt knob, which is used to adjust the radar antennae relative to the horizon. The tilt angle is displayed on the ND. The gain knob, which is used to manually adjust the sensitivity of the receiver. In this case, the word man appears in green under the tilt indication. In the auto position, the radar automatically adjusts the gain to the optimum setting. There are three positions of the mode selector. Weather shows the intensity of precipitation. Weather turbulence shows the turbulence areas in magenta. Map, the radar operates in ground mapping mode. When auto is selected, the predictive wind shear system generates the appropriate visual and oral annunciations. The tilt and gain are automatically controlled for the scanning, but the tilt displayed on the ND indicates the tilt value manually selected on the panel. The A330 family is equipped with standby instruments, which include a standby airspeed indicator, ASI, a standby altimeter, a standby horizon. Moreover, a standby compass is fitted on top of the windshield center post. A deviation card is fitted near the compass. We will now have a closer look at the other instruments. The standby airspeed indicator is fitted with an airspeed pointer and airspeed bugs. The only pilot input to the standby airspeed indicator is the manual setting of the speed bugs. The standby altimeter is fitted with an altitude pointer, an altitude counter, a baroset counter which displays pressure setting in inches of mercury or in hectopascal depending on the option chosen, a baroset knob. The standby horizon is erected by pulling the caging knob. The standby horizon is the only standby instrument requiring an electrical supply. In the event of a total electrical failure, it continues working for approximately 5 minutes. In the event of instrument or power supply failure, a failure flag appears. As part of your walk-around, you would verify the condition, damage, blockage, of the 3 angle of attack AOA probes, the 3+3 captain, first officer and standby static ports. Check that the static ports are clear and the covers are removed. The 3 pitot probes, the 2 total air temperature TAT probes, the radar radome and its latches, navigation antennas on the lower center fuselage. For normal operation, after AC power has been connected to the aircraft, ensure that the IR and ADR push buttons are in their normal lights out position. Then, select the nav position on the 3 IR mode selectors. The alignment process has now started. The on-bat light illuminates amber for a few seconds as a test of the battery circuit. Almost immediately, air data information is shown on both PFDs. On the ECAM memo, the message IRS in align greater than 7 minutes appears. This message tells you that the alignment process has begun. It takes approximately 10 minutes for a full alignment, but the ECAM will only count down from 7 minutes. After approximately 30 seconds, attitude information is displayed on both PFDs. To allow an IRS alignment, you will have to enter the present position in the INET page of the MCDU. To save time, we have already selected this page for you. One method of position entry is to insert a company route. We have inserted the company route JAK TASH into the scratchpad for you. It corresponds in this database to a flight from Jakarta, Indonesia, to Tashkent, Uzbekistan. Select this route in the company route field by selecting LSK1 left. As you can see, this has automatically entered the latitude and longitude position of the Jakarta airfield into the MCDU. This data has been obtained from the aircraft database, and you should confirm that this position is correct by reference to airfield charts. Notice the up and down arrows beside the latitude title. These arrows tell you that the latitude information can be adjusted by using the MCDU slew keys. Press the MCDU slew up key to change the latitude information. No, press the MCDU slew up key. Notice that the latitude figure has been increased by 1/10 of a minute. To adjust the longitude position, select LSK 4 right. Notice that the 2 arrows have now moved across to be alongside the longitude title. The longitude information can be adjusted in a similar manner to the latitude. Press the MCDU slew down key to change the longitude information. Notice that the longitude has been decreased by 1/10 of a minute. Using this method, it is possible to fine-tune the position to, for example, the current gate position. An alternative method to input the present position is to enter the departure and arrival airfields. We have already entered 2 airfields into the scratch pad. Now select these 2 airfields to the From To field by pressing LSK 1 right. This page presents all the flights from Jakarta to Tashkent previously stored in the database. There is no flight already stored between these 2 airports. Now return to the Init page by selecting LSK 6 left. This method has also automatically entered the latitude and longitude position. The position can be adjusted in the same manner as before. Either of these methods brings up the amber Align IRS prompt. Once you have confirmed that the position is correct, you can send it to the ADIRS by selecting the Align IRS prompt. Send the position to the ADIRS. The Align IRS prompt disappears, and the IRS will use this position as their reference to perform alignment. The IRS in Align message on the engine warning display counts down the time remaining until full alignment is completed. We have speeded up this countdown for you. If the position has not been inserted, the countdown will stop at 1 minute. In the MCDU scratch pad, a message, Enter Present Position, appears. Once IRS alignment is complete, all the information on the PFD and ND is available. The IRS in Align message disappears from the engine warning display memo. For the remainder of a normal flight, no further pilot input is required for the ADIRS system. At the end of the flight, you have to check the IRS performance by looking at the drift and residual ground speed. This information is accessed through the Data Index page on the MCDU. This page has already been called up on the MCDU. Call the Position Monitor page now. On this page, you can check the position deviation of the 3 IRSs. For additional information, refer to your documentation. To check the residual ground speed, you have to look at the IRS Monitor page. The Data Index page has already been called up on the MCDU. Call the IRS Monitor page now. No. Select the IRS Monitor page. Let's now look at IRS-1 parameters. Call the IRS-1 page now. From this page, you can check the residual ground speed of IRS-1, then access the other IRSs. For additional information, refer to your documentation. For the flight back, you have to insert a new company route typed for you in the scratch pad. Please insert it in the company route field. On this page, notice the message Reset IRS to Nav. It indicates that you have now to perform a fast alignment of the IRSs. To carry out a fast alignment of the 3 IRSs, you have to momentarily set the 3 mode selectors to off. Select IR1 mode selector to off. Before 5 seconds have elapsed, turn it back to nav. Now turn it back to nav. Fast realignment is now in progress. You should note that if a rotary selector is switched to the off position for more than 5 seconds, a full alignment will commence, lasting up to 10 minutes. With the position now in the MCDU, you can see that the Align IRS prompt has appeared on the MCDU display. After confirming that this is the correct position, it can be sent to the ADIRS. Select LSK 3 right to realign the ADIRS. The actual position has been sent to the ADIRS. The ADIRS will take approximately 3 minutes to realign to the position entered into the MCDU. The ADIRS are now aligned and the flight plan has been entered into the MCDU. Let's see the other operations you have to do concerning the navigation system in a normal flight. VOR1 pointer and data are shown on the ND. Display VOR2 data. The left side of the ND shows information from receiver 1 and the right side from receiver 2. Notice that a small picture of the associated pointer being used is represented close to the name of the corresponding VOR. As the VOR associated data and pointers are displayed, both receivers consider the VOR signal as valid. On the second line, the VOR identifier appears, here Charlie Kilo Golf. On the third line, in green, the DME distance in nautical miles.
To see the nav aids automatically tuned by the FMGEC, we have to call the radio navigation page. Call the radio navigation page. You can see on the radio navigation page that the FMGEC has automatically tuned the VOR Charlie Kilo Golf on both receivers. Select VOR-D push-button switch. The VORs present in the database are now displayed. We will manually select, as a training example, the VOR Tango Kilo Golf. The VOR identifier, TKG, has been typed for you in the scratchpad of the MCDU. Insert it by selecting LSK 1 right. Insert VOR TKG. Notice the VOR identifier in uppercase on the MCDU, indicating a manual selection. On the ND, this is confirmed by a tiny underlined M beside the VOR2 data location. Notice also, as a valid signal has not yet been received from VOR TKG, the associated data and pointer are not shown. Set ILS display on. No. Select ILS push-button switch. No. Select ILS push-button switch. On the PFD, you can check the ILS identifier, India Charlie Golf Lima in this case, the frequency and the course. The course is also indicated on the ND. The check and the selection of the nav aids are now complete. We will carry on with the settings of the altimeters. We will now set the barometer settings on the EFIS control panel. The current QNH is 1007 hectopascal. Set the correct QNH on the EFIS panel. The new QNH is displayed on the EFIS control panel. On the PFD, the QNH is shown and the altitude indication can be checked. Let's assume that we will take off now. During the climb, at transition altitude, here 11,000 feet QNH, the barometric indication will flash on the PFD. You will have to switch the barometric settings to Standard, STD, by pulling the barometer reference selector. Set Baro to STD. No, select the barometer reference selector. STD appears on the EFIS control panel. You can also see the STD indication on the PFD in cyan and yellow boxed. Notice also the selected altitude, which has changed to a flight level indication, flight level 150. Let's assume we have performed the same setting on the standby altimeter. As VOR receiver 2 now receives a valid signal from the TKG VOR, the associated pointer and data are displayed on the ND. As TKG VOR is not equipped with a DME, the DME indication is replaced by green dashes. The indication NAV Accure Upgrade has appeared at the bottom of the ND and in the MCDU scratchpad, meaning that the navigation accuracy level has automatically switched from low to high. We will now see how to make a navigation accuracy check. The objective of the navigation accuracy check is to compare the raw data from the tuned nav aids with the corresponding FM computed data. The SOP recommends to do this periodically in cruise prior to initiating the descent and when entering a terminal approach area. If your aircraft is equipped with GPS primary, no accuracy check is required as long as GPS primary is available. The GPS mode can be checked on the prog page.
If the GPS is no longer primary, the message GPS primary lost is displayed on the ND and in the MCDU scratch pad. Notice that the navigation accuracy level stays at high. Nevertheless, the navigation accuracy has to be verified. The SOP recommends in such a case to perform the comparison on an hourly basis.
This check has to be performed whenever the following cases occur: IRS-only navigation, the prog page displays low accuracy, nav accuracy downgrade message appears on the MCDU and on the ND. To perform this check, you have to use the selected nav aids and display them on the ND. We have set the ND range to 80. The VOR, Sierra Papa Romeo, has been manually tuned on receiver 1. Note that the VOR, Papa Alpha Sierra,
is the two-way point of the flight plan. There are two ways to do this check. The first method is to compare the two-way point distance and bearing, which is FM computed data, with the corresponding NavAid DME distance and bearing. Call the prog page. The second method is to insert a VOR DME ident in the bearing distance 2 field on the prog page, and to compare the computed bearing distance with the raw data on the ND. We have typed the VOR DME ident, SPR, in the scratchpad for you. Insert SPR in bearing distance field. We now have on the prog page the computed bearing and distance to the selected NavAid. The distances shown on the ND and on the prog page can be compared. The last method consists in checking that the raw data needle passes through the blue FMGES generated symbol for the VOR DME and that the position of this symbol corresponds to the DME distance. Whatever method is used, if the error is less than 3 nautical miles, the check is positive, and the FM position is reliable. The SOP recommends to use the ND in ARC or ROSE-NAV mode and manage lateral guidance. If the error is greater than 3 nautical miles, you can consider that the FM position is not reliable. In such a case, the SOP recommends to use raw data for navigation and to monitor it. Let's see what happens when approaching the polar region. At high latitude, or when entering the North Magnetic Polar region, the ADRUs replace magnetic heading by true heading on EFIS and DDRMI. When approaching the polar region, the ADRU triggers a message on the MCDU and ND requesting to change the north reference. Set the north reference push-button switch to true. When true is selected, true heading is displayed on the instruments. The heading value has changed, and a true label is displayed above the heading scale on the PFD and ND. In addition, on the ND, a grid track is displayed and the VOR needles have changed to magenta. The correction indication near the VOR identifier indicates that the VOR data is corrected by the FM. Here, the aircraft is true referenced and the VOR is magnetically referenced. On the MCDU, the bearing or track for each waypoint has also changed to true, as indicated by a T letter near each value. In addition, a message True North Ref is displayed in the memo part of the engine warning display. When out of the polar area, you have to revert to magnetic heading by setting the North Ref push-button switch to off. You are in flight. Everything is normal when suddenly click on the forward arrow to activate the failure. On the engine warning display, read the title of the failure. Notice also the check attitude on both PFDs, indicating that there is a difference in the aircraft attitude displayed to the pilots. There is no ECAM page associated with the ADIRs, so the cruise page remains on the SD. The attitude cross-check demanded by the ECAM procedure is carried out by comparing the PFD attitudes with that of the standby horizon. In this example, the FO's PFD, which shows a different attitude to that given by the captain's PFD and the standby horizon, is likely to be the one at fault. Having identified which PFD is giving the incorrect attitude display, the attitude heading switch should be selected to that side. In this case, the switch must be selected to First Officer on 3 position. The pilot flying will ask you to perform the next ECAM action. Perform ECAM action. IR3 is now supplying the First Officer side. The aircraft attitude on the First Officer PFD is back to normal. Check attitude indications have disappeared. Clear nav. Notice that the ADIR switching memo is displayed as the attitude heading switch is not in normal position. ECAM action completed. We will continue with an ADR1 fault which normally supplies ATC1. Let's assume you are the pilot non-flying. You are in flight, in cruise, and everything is back to normal. Click on the forward arrow to activate the failure. On the engine warning display, read the title of the failure. Notice on the PFD the speed, altitude, Mach and barometric indications are lost. The procedure requests you to switch the air data switch to the Captain on 3 position. The pilot flying will ask you to perform the ECAM actions. You, as pilot non-flying, read and perform ECAM actions. Perform ECAM action. By switching the air data switch to Captain on 3, ADR3 supplies the Captain's PFD and ND instead of the faulty ADR1. ADR1 has to be switched off. Continue ECAM action. The next ECAM action line requests that you set the GPWS off. Continue ECAM action. Notice that the GPWS action line is not removed when the action is performed. After review and confirmation from the pilot flying, clear to see the status page. Clear nav. The status page is displayed for review. A green message advises us that the approach capability is degraded to Cat 3 single only. You can see in the inoperative system column that ADR1, Cat 3 dual and the GPWS are now inoperative. After confirmation from the pilot flying, you can clear the status page. Clear the status page.
No. Press the status key or either clear key.
ECAM action completed. Let's see now a demonstration of an in-flight radio altimeter abnormality. You are the pilot non-flying. You are in descent. Everything is back to normal. Click on the forward arrow to activate the failure. On the engine warning display, read the title of the failure. As there is no associated procedure, after review and confirmation from the pilot flying, clear nav. The status page is displayed, showing inoperative systems and aircraft information. With only one RA, Cat 3 is no longer available. After review and confirmation from the pilot flying, clear status. You are flying an approach manually, with RA2 still faulty. Click on the arrow to activate the failure. On the engine warning display, read the title of the failure. As the GPWS no longer receives data from radio altimeter 1, it is now inoperative and has to be switched off. After confirmation from the pilot flying, perform the ECAM action. Select GPWS System Push Button off. The GPWS action line is not removed when the action is performed. You can now clear nav. The status page is displayed, showing inoperative systems and aircraft information. With both RAs faulty, both APs are lost for approach, as well as the auto callouts and the GPWS. After review and confirmation from the pilot flying, clear status. The ECAM system display automatically reverts to the wheel page, and the status reminder is displayed on the engine warning display. The first part of the navigation abnormal operation is now complete. You will now study how to navigate using the standby navigation keys. Let's assume you are the pilot non-flying, in cruise, and this is one of those days. You have just lost both FMGECs. Click on the forward arrow to continue. Blank MCDU screens with amber FM1 and FM2 annunciator lights and the red Map Not Available message on the ND indicate that a double FMGEC failure has occurred. Here we will focus on the navigation, so we will consider that all the actions concerning the other systems have been performed. As the MCDUs are no longer available for navigation and nav aid tuning, the only navigation capability remaining is radio aid raw data. For this, we need to use the standby nav aid tuning capability of the RMPs. The activation of the standby navigation is achieved by pressing the nav key on RMP1 or RMP2. Select the standby nav on RMP1. The guard is up. Continue. Select the nav key on RMP1. The green nav light illuminates to indicate that RMP1 is now in nav mode. The nav mode has been selected for you on RMP2. The green nav light has illuminated. For nav aid tuning, RMP1 standby nav keys are associated with VOR DME1 and ADF1, while RMP2 keys are associated with VOR DME2 and ADF2. RMP1 or 2 can tune both ILSs at the same time. To illustrate this, we will tune an ILS frequency. The required standby nav key can be selected. Select the standby ILS key. The standby nav ILS key is illuminated. Both windows are now showing the last memorized ILS frequency. Notice also that the selected radio light is now extinguished. We will tune a different ILS. Select ILS frequency 108.9. Press the transfer key. The new ILS frequency is now tuned. Notice that the course is now displayed in the standby course windows. We will adjust it now. Select ILS course to 145. The new ILS course is now set. The tuned ILS is ready for the approach. The setting of the other nav aids, frequency, course, is done in the same way. Note that if an ADF receiver is selected, pressing on the BFO key will activate the beat frequency oscillator. Note, when an RMP is used to tune an ILS DME, the PFDs do not display the DME distance. To use the RMP for communication frequency change, you select the corresponding VHF or HF key without deselecting the NAV key. NAV key has no effect on radio communication selection and must be kept on in order to avoid frequency changes to NAV receivers. We will now review some indications we did not have the opportunity to see when performing the previous procedures. We will see first an ATC unit failure. The code display goes blank and the ATC fail light illuminates when the selected transponder has failed. In this example, transponder 1. System operation may be recovered by selecting the other transponder. Select transponder 2. With the selection of the second transponder, the code reappears in the display and the ATC fail light extinguishes. The ATC TCAS unit is again fully operational. We will continue with the weather radar failure messages. In case of any failure, a message appears on the ND, amber for a radar performance degradation, red when no image is available. The next faulty system is the TCAS. In case of TCAS failure, a TCAS fault message is displayed on the engine warning display and TCAS red flags appear on both PFDs and NDs. Note that there are neither warning lights nor all warnings. We will now study the DDRMI flags. In case of failure, specific flags can appear on the DDRMI. In case of RMI internal failure or power supply loss, all flags are shown. The abnormal operations are now complete.